Hello, everyone, and welcome. So this week I'll continue talking about rotational motion, and I am going to introduce a new concept called angular momentum. And by using the machinery we introduced for angular momentum, we will be able to describe more general rotations, more general than the ones we introduced last week. So let me start. First, let's just start with like a high-level overview. So angular momentum is defined as L is equal to I times omega. And you can compare this to our like linear momentum, in which case P was equal to M times V. So in this case, M is mapped to I, moment of inertia, and linear velocity is mapped to angular velocity omega. So the unit of this angular momentum is kilogram meters squared per second. So if you take the derivative of this object, which is written like this, we can just probably take the derivative of whole thing, and then it's like d omega dt. So you can kind of see this is the torque we introduced last week, and this whole thing can be written as like a total derivative of angular momentum. And this gives us a generalized form of Newton's law for rotational motion. dl dt is equal to torque. So you should compare this also with F is equal to dp dt we introduced in the previous weeks. So from this equation, if you set torque is equal to 0, if there is no torque in the system, that means dl dt, change of angular momentum with time, is 0, which means L itself is constant. That means I times omega is constant. So then we call this conservation of angular momentum. And you should add this conservation to a list of other conservations we introduced last week, specifically conservation of energy, conservation of momentum, and conservation of angular momentum is the third one on this list. So this is actually very useful. Here's an example. If you have ever seen these skaters on TV, so they have this trick. Initially, they start with their arms open, and they have some velocity. Let's say some angular velocity, and then at some point they close their arms to their like bodies, and then you see them like spinning a little faster. Actually, we can explain this with this conservation of angular momentum. So initially, when the arms are open, moment of inertia is large because these masses are like further away from the rotation axis, and there's some omega. But when she closes her arms, I gets smaller, and we know we have to keep I times omega constant. To compensate the smaller I, omega has to increase. That's why she's starting to spin faster. Okay. Maybe we can do this practical example to test our understanding. Here is the example from the book. So a small mass, M, attached to the end of a string revolves in a circle on a frictionless tabletop. The other end of the string passes through a hole, like here, in the table. Initially, the mass revolves with speed v1, 2.4 meters per second, in a circle of radius r1 is equal to 0.80 meters. The string is then pulled slowly through the hole so that the radius is reduced to r2 is equal to 0.48 meters. What is the speed v2 of the mass now? Okay. Maybe this is simple, so I will go ahead and solve. So angular momentum is conserved, so L is constant. So initially L is what? It's equal to M, some V1, and there's some radius R1. And when the string is pulled, M stays the same. There's some V2, and radius goes to R2. We can cancel M's. And we can just solve this for V2, which is equal to R1 over R2 times V1. And if you put the numbers, which is around 4 meters per second. Okay. Basically, you go from this slower speed to higher speed when you decrease the radius from R1 to R2, because you decrease the moment of inertia, to compensate that, you increase the velocity. So the second thing to emphasize is the vector nature of angular momentum. In the previous page, we didn't talk about this, but actually angular momentum is vector. We show it like in a vector over L. And when the rotation axis, when the rotation is around a symmetry axis, then we can actually write an equation like this. L vector is equal to moment of inertia around that axis times the angular velocity vector. And we know how to calculate angular velocity vector from right-hand rule, so we can determine L from that. So maybe we can go ahead and do this example to demonstrate this. So suppose a person stands at the edge of a 6-meter diameter circular platform, which is mounted on a frictionless bearing and has a moment of inertia like 1800 kilogram meter square. The platform is at rest initially, but when the person begins running at speed 4.2 with respect to Earth around its edge, the platform begins to rotate in the opposite direction. Calculate the angular velocity of the platform. Does the hand do work in the previous example? So yes, it does, and you can actually calculate. There'll be some increase in kinetic energy, right? And but the key is this hand, of course, does work, but the force, if you zoom in, force is going through here, and it cannot have any torque on the system. So when there is no torque, that means angular momentum is conserved. That's why we had to rely on to this to solve this problem. That's a good point. Thanks for asking that. Now let's just see this. Initially, maybe I can say that initially angular momentum is what? It's okay. Maybe I can write it nicely. Li is initially so the person is at rest. The platform is at rest. There's no angular momentum, right? Initially, it is 0. And the person starts running at some speed, which we call m times, let's call this v times, and it's some at radius r. So that's the angular momentum coming from the person, and plus there will be an angular momentum on the platform. L, let's call this platform, is equal to 0. And the key is we can actually calculate the direction of this person's angular momentum from right-hand rule. So if this guy is walking like this, we can do like, imagine you are wrapping your fingers around this direction. If you stick your thumb, it's going to be pointing this direction. So angular momentum of person is here. And I think you can imagine that this platform will be moving on the opposite direction, and you can do the right-hand rule to see that platform's angular momentum is like this. But initially, the total angular momentum is 0, so this angular momentum coming from platform should cancel the angular momentum coming from the person. So that's what we are trying to set up. And maybe I can just calculate the magnitudes first and then say the directions. It's going to be something like this. L, but L is equal to what? Okay, take a smaller one. This is going to be I omega, and I is a disk, so it is, actually its moment of inertia is given. So it's I of omega. calculate the angular velocity of the platform, then omega is equal to mvr divided by I. So we can put the numbers, 0.42 radian per second. And L platform points down. So obviously we could also get to this conclusion by thinking about like forces, and the person is exerting some force as he runs and blah blah. But let's just think about another example where this is actually not that trivial. So here is that conceptual example. Your teacher is holding a spinning bicycle wheel while he stands on a stationary frictionless turntable. So this turntable is able to rotate and there's no friction. And he is holding a spinning bicycle wheel. And what will happen if the teacher suddenly flips the bicycle wheel over so that it is spinning in the opposite direction? So what will happen if he suddenly takes his left hand down and his right hand up? Any guesses? Any ideas? So the platform will turn to the opposite direction of the wheel in order to conserve the momentum. Exactly. Thank you. He will spin counterclockwise opposite. Yes, exactly, right? So initially there's some L, and this L should be conserved no matter what, because we know there is no external torque on this system, which is closed. So when he flips, so initially it's like rotating like this way. So right-hand rule tells me this. But if he flips, it's going to be rotating this way. And right-hand rule tells me that it's going to be pointing this way. But I know the total angular momentum should be conserved. So something should compensate this. And what will be compensating this is this platform itself is going to start rotating along with the teacher. So then there will be an angular momentum on the opposite direction. So if you sum this with this, you will reach to this initial angular momentum. Okay. So the answer is teacher and the platform will start rotating. What is that? That's counterclockwise. So to make all these things systematic, we have to introduce a mathematical machinery the same way we introduce this dot product. And here we'll introduce so-called vector cross product. And from this, we will define torque vector as a cross product. First, let's talk about cross product. So C is equal to, like we write it like this, A cross B. And A is a vector, B is a vector, and C is also a vector here. And the way we find the direction of C is we put our fingers along A, the first one, this like which one comes first is important. So we put our fingers along the first one, and we imagine we close our fingers like this. So as we do this with our hand, we also imagine sticking our thumb out. Then this thumb will be pointing along C, okay? So fingers goes from A to B, and if you stick out the thumb, it's going to be the direction of C. So this kind of definition satisfies this. C is equal to A times B times sine theta for theta less than 180 degrees, the angle between A and B, and it is direction found by right-hand rule. These two things are important. So we can also define this cross product in terms of components of A and B. And imagine A is written like this, AX, AY, and AZ, and B is written like BX, BY, and BZ. and the cross product C is found from this so-called determinant rule. This is not actually a determinant, but it kind of looks like determinant. And the way we do this is like as follows. So in the first row, we write the unit vectors in order, I, J, and K. In the second row, we write the components of the first vector, AX, AY, and AZ. And in the third row, we write the components of the second vector, BX, BY, and BZ. Now we can calculate this A cross B as follows. We just first put plus and minus and plus here. And the plus one will come with plus I hat. And we imagine closing this column, whichever column we are. And of course, we close this one. And we have a square here. And in the square, we multiply these diagonals, AY, BZ, and subtract from these diagonals, AZ, BY. Okay? So let me write this. AY, BZ minus AZ, BY. Now I go to the second one. Second one comes with minus, and it is J. So I put minus J hat. And I close this column and this row, and I have this, imagine combine this column with this column to get a square, then again, this times this, minus this times this, okay? And let me write this. This is AX, BZ minus AZ, BX. And finally, I came to the last column. This is plus, and this is K. So this is plus and K. Open the parentheses. Now I close this column, and again, the first row, I have this square here again. And this is A times BY, AY times BX. Let's write this one too. X, BY minus AY, BX. So if you do this systematically, you'll get the right result for cross product. And I suggest you work on this if this is the first time you see this. So there are some properties related to this cross product. First one is, of course, A cross A is equal to 0. So if both vectors are in the same direction, the cross product will be 0. You can see it from here, right? If the angle between these two is 0, as in A and A, then the cross product will be 0. So I said the order is important. So A cross B is actually equal to minus B cross A. So if you change places, you get a minus. So there's like distributive law, A cross B plus C is equal to A cross B plus A cross C. And finally, this derivative X in a funny way. So that's not very confusing, but sometimes we can get it wrong. So let's just write it here. D dt A cross B is the A dt cross B plus A cross dB dt. Okay, this is like a chain rule applied to a cross product. So now that's all you need for cross products. So now we can introduce torque, and we define the torque as a cross product between R and force. So you can see from here, if you write torque as like F R sine theta, the previously defined, I think we defined it last week, torque is satisfied. You can think of this like F times R perpendicular or R times F perpendicular. Let's check. And the direction also obeys the right-hand rule because cross product obeys the right-hand rule. So that's the direction also matched. So that's a definition of torque. And if you have like a system of particles, total torque is, since each one is a vector, we can find the total torque as a vectorial sum like this. So that was the first cross product we introduced. Now there is another one, and that's the angular momentum. And for this, let's first start with a particle like this here. And the definition of angular momentum in terms of cross product is like this. L is equal to R cross P. There's some R. There's some, I don't know, some direction P. Then if you take their crosses, you get angular momentum. And you can define it like this, either R perpendicular times P or R times P perpendicular, which is the same thing. So it's basically PR sine theta. And if you take the time derivative of this object, dl dt, it's like d dt of R cross P. So, okay, maybe I can do this for you to see. So this whole thing is equal to dr dt cross P plus, I'm just using this rule we just introduced here, and R cross dp dt, but this one, the rdt is what? Can anybody see? I mean, what's the definition of the rdt? V, right? Yes, thank you. And this one is m times v, but v cross v, we just showed it is 0, so this whole thing is going to be 0. And this one, derivative of p is equal to what? dp dt? Newton's law, right? It's going to be force. So I can just put force here. Then dl dt is r, okay, this whole thing is r cross f. Then that's equal to torque, okay? And you should compare it with the linear case. In the linear momentum case, we had like dp dt is equal to f. In the angular momentum case, dl dt is equal to torque. So in an inertial reference frame, okay? So that was for one particle. If you have more than one particle, you can just sum them up. Like you can have L1, L2 up to n, and tau 1, tau 2 up to tau n. So the net torque is vectorial sum of each one. And on the other side, we can just take the derivatives of each one and then sum them up, right? But now here, let's just see, like imagine there are like so many of them distributed, and there's some, well, a lot of forces, but let's just isolate two, M1 and M2, and look at their forces. And let's see if we can do any simplification. So first, I want to put M1 to R1 and M2 to R2. And I want to look at the force on 1 by 2, which is F12, or force on 2 by 1, which is F21. So I can write torque on 1. Torque on 1 due to the force by 2 is equal to R1 cross F12. And torque on 2 due to the force by 1 is equal to R2, like R2 times crossed with force, crossed with F21. Now let's sum these two guys. So this is R1 cross F12 plus R2 cross F21. But we know from Newton's third law, this is an action-reaction pair. So F12 is equal to minus F21. So we can write this. So this is equal to R1 minus R2, then F12. This is cross product. So let's look at this. Let's look at this object. This object, R1 minus R2. Okay, there's another vector here. This object and this object. So F12 is along this direction. And R1 minus R2, R1 is this. Minus R2, so R2 is this. So minus R2 is on the opposite direction. So R1 minus R2 is then along this direction. So it's actually this direction, but it doesn't matter. But the key is, since the angle between these two guys is 0, like F12 points along this, so this whole thing is going to be 0. So we then reach this important conclusion. So dl dt, sum over all particles, is equal to sum over all external torques. So we neglect the internal torques. And this is Newton's second law for rotational motion for a system of particles. So this is for, like I said, inertial frame. But if we are concerned with center of mass and the motion around center of mass, there's actually a stronger statement like this. dl center of mass by dt is equal to tau net torques around center of mass. And this sentence is true even if center of mass is accelerating. And we can actually show this. So for this, okay, I need to introduce some first labeling. So my center of mass, I show it with R of center of mass. And there may be many particles, but I am focusing on only one of them, and let's call it M of I. And the location of M of I is we call R of I, like this. And the location of M of I with respect to center of mass is R of I with star. So star means in a coordinate system where center of mass is in the origin. So we can write it like this, right? Ri is equal to R center of mass plus R star. And if you take the derivative of each term here, you'll have Vi is equal to V center of mass plus Vi star. So like I said, since center of mass is origin, at least in the coordinate system where center of mass is the origin, you also have this result. If you calculate center of mass, it is sum over all Ri stars in terms of star coordinates, and it should be 0 because that's the origin by definition. And now I'm ready to prove this sentence. So I start with dl, the time derivative of L center of mass. And this L center of mass is, I think we just define it to be like R star R cross P, but in the star coordinates. So let me put this derivative. So this is sum over I, dRi star dt cross pi star plus sum over all I Ri star cross dp star dt. Now this one is again Vi star. This one is again I times Vi star. So a cross product with itself is always 0, so we can cross this term out. We can cancel that. And for the second one, I want to use, okay, so Pi is equal to Mi. Okay, I want to use this equation. So this is Mi Vi minus Mi V center of mass. These are both vectors. Let me take derivatives of, okay, so there's like a substitute, okay. I substitute this P to here. And if I do this, I'll get something like this. Sum over all Ri star, okay, cross Mi dVi dt and minus sum over all Ri star Let's put mi cross the what did I do? The center of mass over dt as a vector. Now I see two things. First, let's just start with this one. So dvi dti is a of I, and mi times a of I is force on ith particle as a vector. That's one thing. And here I see this object does not have any indices, so I can take the parentheses and first calculate this. But if I calculate this, I know this is R center of mass by definition, but this is the origin in our coordinate system, so this is equal to be 0. So then we reach this important result. Then this dl dt is equal to sum of all I are I star crossed with fi. But what is this? This is, okay, if I look at this, our I star and force on I, if I sum all over these guys, I have the torque on I like this. So this is I, torque on I in the center of mass coordinate. So this is equal to total torque in the center of mass coordinate. Okay? Okay. So this was for a point particle. And now let's just consider a solid object, which we call like rigid object. And let's try to calculate its angular momentum as a vector. And for this, I want to focus on this cylindrical example. Okay, there's like a cylinder with some height, and this cylinder is rotating around its like symmetry axis like this. And from right-hand rule, we know omega is going to be pointing along z direction. And I want to calculate the angular momentum of this object along this vector omega. And for this, let's just show it. Let's just, for notational convenience, let's call it L of omega. L of omega, total angular momentum, is some complicated, maybe, we don't know yet, but maybe some L, we want to calculate its projection on omega, like this. Okay. And for this, we can start with a little bit of chunk here. Let this be that chunk. It could be here. Here, it doesn't really matter. And I want to calculate angular momentum of this chunk, and I want to take its projection along the omega. That's what this notation means. Now, if this cylinder is rotating like this, I know this particle is rotating like this with this momentum, and its position is like this. So then I can calculate the angular momentum like this. This is R cross P, and I need to project it on the omega. And its projection to omega is like, at least projection to this axis. And the way I can do this is like what? It's like, so I think I can calculate this from the right-hand rule, right? Our right-hand rule says that your fingers start from here and goes through here. And if you stick your thumb out, like imagine your hand, fingers first, and then fingers curl. And then if you stick your thumb out, your thumb will point along this direction, which is going to be perpendicular to both of these. And you can see that's the L here. That's the L here. And that's the L here. But I want to take the projection of this L along this axis. And if this L, if you extend it like this and put some angle theta here, or phi, and this angle is going to be phi too. But this is phi, this whole angle is 90, then this is 90 minus phi. And this whole angle is 90, then this is also phi. Okay? You can just visualize the geometry and you can see this. If this is phi, this is also phi, and this is also phi. So let's use this. So then, so L is what? R I. So this is like what? VI, and I need to take the projection, which is going to be cosine phi. Okay. And here I know, okay, I know this times cosine phi is going to give me this Ri. Let me write this. This part is going to be Ri. And Vi, so this Vi is also equal to, if I have omega angular velocity and my distance to the axis is r, so that's also Ri. So this whole thing is equal to Ri squared. Let me see. I have m, I have Ri squared and omega. Now, if you sum over all particles, then that means, okay, let's write it like this. L of omega is equal to sum over all particles, Li of omega, and this is equal to sum over, okay, this is Mi, this is I, Mi, Ri squared times omega, but this is I as expected, we have got I times omega. So the upshot is that the angular momentum's projection along this axis is equal to I times omega as expected. So we calculated one component, and now I want to calculate the perpendicular component, the component that's perpendicular to this component. And for this, I need to look at my vectors again. So this point particle, from right-hand rule, I found that was the angular momentum vector, and I take care of this component. Now I am left with this component. But if I really pay attention to this component, when I look at the other side of the cylinder, there's exactly a symmetrical component which points in the opposite direction, whereas their LIs are pointing in the same direction. So I say this is equal and opposite to this, so these two will cancel each other. And from this, I say that the component of angular momentum lying in the plane is equal to 0. So this already proves L as a vector is equal to I, which is moment of inertia along this axis, times omega as a vector, okay? And this is like, I want to emphasize one more time, if the rotation is along a symmetry axis. We would not be able to prove this if this was not a symmetry axis, if this cancellation did not take place. And finally, you can use this torque is equal to dLdt, and you can calculate the torque around this axis, and it's going to be d dt I omega, and I is constant, so this is going to be equal to I times alpha. Okay. So, okay, maybe, so this is probably all the, okay, let me see the material. This is all the theoretical exposition. From now on, we can show a couple of examples and see these things in practice. But before that, I want to give like a 5-minute break. So here's the example. So an Atwood machine consists of two masses, MA and MB, which are connected by an inelastic cord of negligible mass, this guy, that passes through the pulley like this, okay? And if the pulley has radius r naught and moment of inertia I about its axle, determine the acceleration of masses MA and MB and compare it to the situation where moment of inertia of the pulley is ignored. Let's write this. Torque is equal to dl dt, or this is going to be I times omega. But for this case, I think we know the directions, so we can just simplify our lives a little bit. But the important thing we have to be careful about is this is the moment of inertia is due to pulley and MA and MB. And torque is due to MA and MB. Okay, so maybe I can start with a calculation of torque. How do I calculate torque? There's some weight mg on B, there's some mg on A. So this one is pulling down, this one is pulling down. Obviously, problem tells us this is heavier, so this whole thing is going to be going down. But the torque here is on this direction, which is clockwise, whereas the torque on here is counterclockwise. So we take this, I think we can take any one positive and then the other one will be negative. So I'll take this one positive. So this is going to be MB times G times R naught. This is torque from the first one minus MA times G times R naught. So this is total torque. Now I will write I pulley times alpha, or maybe I can write it like this. Total I is I pulley plus, so the contribution coming from this mass, which is MA, and it is perpendicular distance is R naught, and square is R naught squared. So this is MA R naught squared, and contribution coming from this guy, MB, is perpendicular distance is also R naught. So I'll just write MB R naught squared. So this whole thing is, just to remind you, the total moment of inertia should be equal to alpha. And once we have alpha, we know A is equal to alpha times R naught. Okay, let's solve this for alpha is equal to MB minus MA, this whole thing divided by, what is it going to be like? So it is I, okay, this is MA, MB, G times R naught, I plus MA plus MB R naught squared. Maybe we can take this R naught squared outside. So this is R naught squared. And delete this. Now I don't need parentheses, so I'll also delete the parentheses. And I will put this R naught to here. And this one cancel with this one. And alpha is equal to MB minus MA divided by I over R naught squared plus MB plus MA times, I think, G over R. Then A is equal to MB minus MA divided by I over R naught squared plus MB plus MA. Why didn't we use the tension in the rope in the equations? I used the tension, right? So I said, so of course you can go ahead and do the tension, but I just looked at the total system like this. So this is my system. And in my system, I am calculating the torque. And torque is coming from gravity. And the first one is acting on here, pulling down. And the other one is acting here, pulling down. And I know the amount of torque. So this is just force times perpendicular distance, or F cross R. So this is F, this is R. It's here, or sorry, okay, this one is here, and the other one is here. So that's it. So is that clear? So when we look at the problem from a rotational point of view, that actually simplified it. That's why we could write it like this in a couple of lines. Oh, G is missing. Oh, okay. Sorry. Thanks for this. Okay, got it. And now the problem is asking us to compare it to the situation where the moment of inertia pulley is ignored. So if I is ignored, obviously A will be bigger. If you ignore I, if you put I is equal to 0, obviously you have a smaller denominator, then A will increase. All right, then, okay, let's continue. So here I want to talk about this conceptual example. So suppose you are holding a bicycle wheel by a handle like this. There's like some handle, and in that handle there's like bicycle wheel, as in figure 17, this figure. The wheel is spinning rapidly, so its angular momentum L points horizontally as shown, like this. So this is like rotating. I do right-hand rule. Imagine curling your fingers like this, and your thumb will be like this. Good. Now, you suddenly try to tilt the axle upward, as shown by the dashed line. Like you want to tilt like this a little bit. You want to tilt this L to like here, so that center of mass moves vertically. So you expect the wheel to go up, and it would if it weren't rotating, but it unexpectedly is first right. Explain. So maybe I can turn this question to a kind of yes or no question. First, let's start with the wheel not rotating, okay? Okay, so first, wheel not rotating. Let's start with this case. And obviously the question is kind of implying that you are going to give a force like this. So let's just say that we always apply a force like this, F down, okay? And F is down. And I want to ask you, so if you push this wheel from here down, in which direction this axle will go up? Is it going to go up or down, or like this, or like this? Any answers? It's going to go up, right? Good. So axle tip will go up. Now wheel is rotating. Okay. And now let's also assume F is down. And my question is, so you have this F down, wheel is rotating, and in which direction L will point in this case? Is it going to go up or down, or along x, or minus x. Okay, some experienced answers. Anybody saying z or minus z? So, okay, maybe I can tell you the answer. For this, we cannot just like say that it's so force is down, it goes up, right? We cannot say that. So we have to look at this equation. Torque as a vector is equal to dl dt. Or if we want, you can think of like dl dt. So then, so the direction of L will be the direction of torque, or direction of change in L is going to be direction of torque. And let's calculate the torque. The torque is R cross P, R cross F. And if I look at R, so R is this, R, and F is this, F. So then R cross F is going to be along here, X direction. Okay? So then R cross F is along X, or I think we said plus I direction. Then delta L is also I direction. What this means is, so this tip is not going to go like this, but it is going to go like this, along this direction. I think your book shows it like this, so this is delta L. And that's a little bit, not intuitive, because normally if we push things down, the tip is supposed to go up, like so. And the reason for this kind of odd behavior is vector nature of angular momentum. Any questions here? Okay, so let's just focus on this vector nature of angular momentum a little bit more. So I want to emphasize, so this kind of equations, L is equal to I times omega with vectors, works only for rotations around a symmetry axis through the center of mass. And all objects, whether it's symmetrical or not, I mean, so far we were looking at symmetrical things, but all objects have like 3 such symmetry axes, and these are called principal axes. So now I want to show you the violation of this kind of equation in a practical example. And let's think of this example, so which is given in your book with some explanation, but I tried to turn it into a problem. So maybe I clean up. So here is the problem. So you have a stick like this with length RA plus RB, and at the end of the stick there are 2 masses, MA and MB. And this stick is fixed on another stick with some angle phi. And this second stick is stabilized with these bearings, and this whole thing can rotate like this. Okay, maybe I can show you. So this mass M can rotate like this, and this mass B can rotate like this. Okay, and we neglect the mass of the rod. So this rod, we assume it's massless. I think this one doesn't matter, but we can also assume it massless. So here I want to calculate first L of the system and compare it to omega. Okay, so let's start with this. So maybe I can ask you, in which direction do you think omega points? So this one is going like this. Okay, maybe I can use a better color. So let's find so this one is going like this. And this one is going like this. So I can use the right-hand rule to find right? To find omega, and omega is basically here. It's already given, right? Omega is along z direction. So omega, okay, maybe I can do this. Omega is along z. Now I want to find angular momentum L. And this L has two components, LA coming from A and LB coming from B. Now I can look at A, so it's R, so my origin is here. And L is equal to R cross P, so R is this, and P is M times V. This is like, at this moment, it's out of page. If you like, you can think of like this. Okay, maybe I can draw it like this. It is out of page, and this is R. So this is R cross P, so this is going to be LA, right? This is the first L. And similarly, this is into the page. So I can start from R, curl my fingers into the page, then my thumb will be this, so this is LB. So clearly, L is not parallel to omega. Okay? And if you sum this and this, your L is going to be something with some angle here, which is, okay, we can actually calculate that angle too. So I think if this is phi, this is going to be perpendicular. So this is 90 minus phi. This is 90 minus phi. That's the angular momentum makes with omega. And B, calculate the direction of torque. So B, how do I calculate the torque direction here? Maybe I can try to calculate torque, first direction, and then its magnitude. Any ideas? What should I look at to calculate the torque? dl dt, right? Thank you. So this is going to be dl dt. Then I need to look at the change of L. So I need to look at how much L changes from this geometry. Now, so this L has two components. So this L has this component. Maybe I can show it with, let me see. Okay. Maybe I can show it with, so there is like a orange component, and there is also a, I don't know, a purple component, right? So this L has an orange component and purple component. Obviously, as the rotation takes place, orange component stays the same. So I need to focus on the purple component. And the purple component is L, okay. So this times sine of this angle is going to be cosine of this angle. So this is going to be L times cosine phi. So let's now look at this figure from top. If you do this, here's what you see. This purple is going to be something like this. And it's the magnitude is L times cosine phi. That's what we found. Now, in a little bit time later, this purple component is going to tilt because these guys are rotating. This is rotating. This is rotating. So then L will also rotate, but only this component will rotate because it's the other one is always perpendicular to the rotation axis, rotation plane. So here, this is also L cosine phi, and there's like some delta L. Okay. Now from that purple component, I can calculate delta L, at least its magnitude. delta L is equal to L times cosine phi times d theta. So whatever this angle is, d theta. But since the rotation, okay, d theta dt is omega, then d theta is omega dt. So let's put this in L cosine phi omega dt. Then dl dt, which is equal to torque, is equal to L omega cosine phi. And it is, at least at the moment this picture is taken, it is pointing into the page. Okay. Now C, find torque in terms of I, omega, and phi. Let's do this. C. So first I need to calculate, okay, so I already calculated torque. I need to calculate L. And I need to calculate, since we are trying to find it in terms of I need to calculate I. Maybe I can first start with I because it's easier. I is, okay, it was like what? Mi Ri squared. So it's going to be Ma Ra times sine phi squared plus Mb times Rb squared. I think sine squared phi. Okay. Now L is okay. Now I can use this MA VA RA, right? MA VA RA. So it's like R cross P. So I have R and I have MV, and is that it? Yes. Okay. Plus B VB RB. But now let's write VA and VB. VA is equal to omega times, okay, omega times perpendicular distance. This is going to be R, okay, RA is what? This is RA times sine phi, and VB is equal to omega times RB times sine phi. Then this is equal to MA. So one RA here, one RA here, RA squared times, okay, maybe I can take inside the parentheses because I don't want to write these guys again and again. So this is plus MB RB squared times omega times sine phi. Okay, good. Now I want to write L in terms of I. So then L is equal to, so I just, okay, so this thing is equal to MA RA squared plus MB RB squared times sine squared phi. So L is equal to basically this I, and I need to divide it by sine phi, so that I have, okay, good. And I have omega, okay, good. I got everything, so now I can put this in terms of torque. So then torque is equal to I over sine phi omega times cosine phi. Then torque is I omega squared over something like this, tangent phi. Okay. So you can see it's like a little bit like non-trivial relation. Torque is equal to omega squared I, and there's some angular relation. And we can also see directions also need some attention. And finally, direction of omega is not the direction of L. So this is the message of this problem. And I hope that I convince you that when these rotation problems are thrown at you, just be careful with vectors and sit down and calculate every single object one by one like this. Okay, any questions? Is it general formula for L? Which one? I omega. But in general, this is also not the case, right? I mean, L. So the most general formula for L is this. L is equal to R cross P. And if you have more than one particle, or if you have a system, you have to sum them up. So this is as general as you can get. That's always true. But things like this, L is equal to I omega, is not always true. So do not jump into these things. I mean, most of the time they are true and we can use it, but we have to be careful. And when you have a rotating object like this, for example, in this case, it's true, right? But in this case, it's not. So this L is equal to I omega works only for rotations around a symmetry axis that goes through center of mass. So this rotation is through this axis. It actually, we don't know if it's the center of mass. Since we didn't say MA is equal to MB, it's likely this is not going through center of mass, but also it's not a symmetry axis, right? A symmetry axis would be like this, or into the page. And of course, the location of this point, the symmetry axis point, depends on MA and MB. So basically, this is not true for this equation. Thanks for asking that. Okay, let's continue. So this conservation of angular momentum, we can actually state it in the vectorial form, like in the case of dp dt is equal to force. We said that if there's zero external force, momentum was conserved as a vector. The p vector dt was equal to 0, then p vector was constant. Here we can do the same thing similarly. If tau external as a vector is 0, then L as a vector is constant. It has 0 derivative, and that constant is implying a conserved angular momentum. Maybe we can see this in practice by using this Kepler's second law. And let me read the question. Kepler's second law states that each planet moves so that the line from the sun to the planet sweeps out equal areas in equal times. So using conservation of angular momentum, show this. So let's first say what is the angular momentum, right? L is equal to, okay, R cross P. This is equal to, I don't know, it's like R m v times sine theta, right? And we say this is constant. So conservation of angular momentum. So we want to use this and we want to derive this Kepler's second law. And let's see what it is. It's like the A, basically if you sweep equal areas in equal time, that means dA dt, constant, right? Or maybe I can first calculate dA and see if dA dt is constant. So dA, let's look at this. So in an infinitesimal time, you go from, so this be sun, that's the planet. After a little bit of time, you go with some velocity v dt, this much, and you need to calculate this area. Okay, but we know how to calculate area of triangles. It's like the base, which is r, times height, which may or may not be inside the triangle, times 1/2. And height is what? This times sine is going to be height. So this is going to be 1/2 r v times dt times sine theta. From this, I already see dA dt is equal to 1/2 r v sine theta. But if I use this result I just found here, this thing is going to be what? L over, what is it? It's like RV sine L over 2m. Since L is constant, L over 2m is also constant. So we proved what we wanted. Simple, right? This could be a little bit more involved if you don't use an angular momentum like this. But angular momentum makes our lives really easy. Like it's like a three-liner, if you like. Here's another example. So a bullet of mass m moving with velocity v strikes and becomes embedded at the edge of a cylinder of mass m and radius r naught, as shown in this figure. The cylinder, initially at rest, begins to rotate about its symmetry axis, which remains fixed in position. Assuming no frictional torque, what is the angular velocity of the cylinder after this collision? And is the kinetic energy conserved? Maybe we can think about all the conservation laws. First, let's start with linear momentum. Is linear momentum conserved in this problem? So P total, is it constant? No, right? Why? Exactly. So if you want, you can think of like this, like it's fixed. It's fixed means, I don't know, maybe there's like a nail here, and this nail is in contact with the disk at all times. And there must be a contact force here if you try to move this disk. And if there is a force, there cannot be a momentum conservation. Okay? So P total is not constant. Linear momentum is not conserved. Conserved. Okay. Now let's come to angular momentum. Is angular momentum conserved? Yes. Why? Exactly. There is no torque. The only force could be from that fixed point. Yes, that could be a force, but its torque will be zero because R is zero, right? There cannot be any torque around this point, and you cannot turn a wheel by applying a force in its like center. So then angular momentum is conserved since torque is zero. Then we can use this to find the velocity after the collision. So initial angular momentum is what? Before the collision, I have like R cross P, right? It's like mv r naught initially. And finally, it is going to be again some v prime r naught. This is the bullet contribution. And there will be some, I don't know, some cylinder has mass m and radius r, so it's like 1/2 m r0 squared times alpha, but alpha is equal to, sorry, not alpha, omega is equal to v prime over r naught, right? So basically, this bullet here will have a v prime, and that v prime will be related to the angular rotation of the disk, which is omega, and this omega is equal to v prime over r naught. So now we can solve this equation for v prime. V prime is equal to, okay, let's first clean up if we can. So let me take this color. So this r naught and this r naught. And I have 1, 2, and 3. Then v prime is equal to m over m plus 1/2 m times v. Then omega is just divide this by rm over m plus 1/2 m times v over r naught. So this one, I think I can write a little close. Okay. There's a comma in between. And now let's come to this energy conservation. Is, okay, maybe, should I say kinetic energy? Maybe. Is kinetic energy conserved? Any ideas? Is kinetic energy conserved? No, right? How do we see this? So we can see this by calculating the change in kinetic energy. Let's calculate the change in kinetic energy. Delta K is equal to K final, which is the 1/2 m v prime squared. This is from bullet, plus 1/2 I omega prime squared. This is from the disk, and subtract the initial one, which is 1/2 m v squared. Okay. So if I do this, this is going to be, okay, 1/2. So this one we already said, okay, let's open this up. 1/2 m r0 squared. This one is v prime squared over r0 squared. So this one will cancel with this one. So the thing will be 1/2 m plus 1/2 m times v prime squared, but v prime squared is equal to where? It's here, right? V prime squared, it's m squared m plus 1/2 m squared v squared, and we need to subtract this object from the whole thing, which is minus 1/2, or actually I can, yeah, m v squared. Okay, I think I can do this. So this is equal to, I can take parentheses 1/2 m v squared. So there's some, I see some cancellation here, this. So if I take this, this is m squared. Okay, I took m outside, so this is m divided by m plus 1/2 m minus, seems to be minus 1. Yes. And this is equal to 1/2 m v squared. Okay, I can actually calculate this. This is m minus 1/2 m over m plus 1/2 m. These guys cancel. So this whole result is actually equal to minus 1/4 m over m plus 1/2 m times v squared. Okay, got it. So this one is positive, this guy is positive, this guy is positive, and there's an overall minus sign. So this thing is less than 0. What this means is kinetic energy decreases. Okay, this is an inelastic collision. So I think that's all for me then. If you have questions, let's talk about your questions. If not, thanks for listening and thanks for being here.